Okay, welcome to the last chapter in the course. Here we're going to talk about light, and we're going to talk about mirrors and lenses. So it's going to build on what we talked about with waves in a spring, waves in water, and now let's talk about light as a wave and some applications to do with that. So, some reading you're going to have to do from the notes. I want you to read these guys right here, all the different properties of light, some applications, some properties of materials that either will transmit or reflect light, the light spectrum. Here's some application questions: diffraction and refraction of light. And let's start here to do with a application. Okay, so if you have any questions about the first couple of things, let me know via email, or if you see me around, if you go to the school I teach at. So here we go, images in a pinhole camera, and this is going to take advantage of one little fact here that you should underline, or I already have it bolded, is that light travels in straight lines. Okay, this is an important property to commit to memory, because when it reflects things, you actually can predict where it will reflect to, where it will hit, and because of this you can actually capture light onto a screen to get an image. Here we're going to go with the most basic and original camera you can think of, and you can make this camera very quickly. If you have a Pringles box, just take it, poke a hole in the lid, and you actually basically just made a pinhole camera. So what does this mean? Well, basically, it's a box like this with a hole. If the hole's pretty fine, light will come in and it will get captured onto a screen, like a theater screen. Okay? Then there'll be a person right here. The screen will be translucent. Okay? Translucent, so they'll be able to see this image. Okay? And this image will be upside down in pinhole cameras because light travels in straight lines. So basically how this works, say you have the sun here. Light comes from the sun, hits the tree in all different spots, right? So if you're standing here, you can see the tree because it's bouncing off the tree and going into your eyeball. Now if you set a camera down, okay, if you set a camera down somewhere next to the tree, then here's what happens. Light rays are shooting out off this tree in all directions, but we, for simplicity's sake, I'm going to only show a few of the light rays, and that will be these two right here. Okay, so in other words, when one light ray hits this, it will so happen, okay, to go right through the hole in the camera, and that's the top of the tree, which will hit the bottom of the screen. The bottom of the tree will hit the top of the screen. Therefore, this is inverted. Okay, the image is inverted. Now your eye actually uses a lens, but your eyeball, the image in the back of your retina, is also inverted, and your brain will flip this image. So that's kind of interesting. We'll get to that later. But pinhole cameras do not flip the image, obviously. So what you see is an inverted little tree. Okay, so what we can do, this is kind of like a basic application, is depending on the size of the pinhole camera, the distance from the image to the hole, also the size of the tree, and this distance right here to the camera, you can actually predict, first you could predict how big the object is, you could predict how big the image is, you could tell what the distance is from the tree or the object to the camera, and it's summarized in a formula that is probably quite familiar to you, and that is a ratio formula, basically saying the height of the image, you should read this, over the height of the object is equal to the distance of the image from the pinhole over the distance of the object from the pinhole. So here's an image showing you this. This would be the object right here. Object. And here is the pinhole camera. If I was to draw it. There's the pinhole camera. Okay. So here's the distance to the image from the pinhole. D2 is the distance from the object to the camera, to the pinhole. And the height of the image is at the back. So you need to know 3 of them to solve for just one. In other words, what's most common is you don't know the height of the object. That's kind of the purpose. You can get the distance. So say it's a tree. You can get the distance from, this is actually kind of interesting. If you think about this, you could get the height of a tree just by putting a camera in front. Then you could very simply measure that distance. You get an image, you measure the image height. You obviously will know the distance from the pinhole to the back, and there you can get a rough estimate, depending on how level this distance is, of the height of the object. Pretty neat. So I gave you one example of this. This is very similar to this formula. Okay, I'll just write here. Similar to your refraction formula from the previous section. The algebra will be the same, so there's really nothing new here. How you tell the difference, of course, between this and refraction is this is using a pinhole camera. Okay, determine the height of the image produced by an object that is 12.2 meters in height. That is 19.7 meters from a camera with a lens to film length of 38 millimeters. So here we go. I actually did this question for you in your notes. So I wrote out the formula, which is that. I allocated my variables accordingly. Okay, it actually doesn't really matter if you make all the 1s the image and all the 2s the object. That's typically what I do. So we're looking for height of the image, so that's h1. So maybe I'll put this 1s are image, 2s are object. Okay? You have to convert this millimeters to meters, so keep that in mind. Everything has to be in the same distance unit. I'll keep scrolling down here. New little technique. You plug it in accordingly, right? You're looking for h1, so everything else goes in accordingly, and then you just solve. And how I solve this, hopefully you're following along here, is I multiplied both sides by 12.2. Oh, that's way off the screen, sorry. By 12.2. And that is game over. This comes out to be an answer of 24 millimeters. I didn't ask for you to put it in a certain unit. If I don't, you can put it in whatever. You can keep it in this or convert it back to this because I gave it the image originally to that one. Okay, so that is pinhole cameras. Moving along, hopefully you read through this. This is important to watch these videos. They're cool. And they give you some inside info about the speed of light and its history. Already talked about history of light if you watched the video at the start. Okay, but basically you need to commit this value to memory. This is the speed of light in a vacuum, which means in the absence of an atmosphere or any kind of gas. Okay, total space. It moves at an enormous speed, 3.0 times 10 to the 8 meters per second, which is really fast. Okay, and think about this. Imagine how far light traveling at this speed could travel in 1 year. It would be really far, and it actually is this length, 9.46 times 10 to the 15 meters. Distance so big that's hard to fathom. Okay, both are constant values. These are constants. You need to commit them to memory. Actually, you don't need to commit them to memory. I'll actually give them to you in a formula sheet, but you need to be aware that they do not change. Okay, hence the reason they're constant. So I gave you a question to do with that. Don't forget about this formula because we're going to use it on the practice problem right now. Our classic distance over time equals velocity. Here we go. How much time would be required for a spaceship traveling at 60.0 times 10 to the 4 kilometers per hour, an enormous speed, to reach the closest known star, Proxima Centauri, 4.3 light years away? By the way, this speed is, I don't want to say something wrong. Let me just write this out in decimal notation. Yeah, I was going to be wrong. Okay, so here we go. Your velocity is 600,000 kilometers per hour. I was going to say it's as fast as the Saturn V rocket went to the moon, but I'm off by a factor of 10. The Saturn V rocket went roughly 55,000 kilometers per hour. Okay, so this is 10 times faster. And we probably can make things that will go that fast eventually. Now, here's the key. When it says light years, most people think that's time. But look, I'm looking for time. Light year is a measure of distance. Important to note. Therefore, the distance is 4.3 light years, which is 4.3 times 9.46 times 10 to the 15 meters from the slide previous. So there you go. You need to convert it to meters for now. That comes out to be something large. I'll write down everything. I'm actually going to take this and divide it by 1,000 to convert it to kilometers. The reason I'm converting it to kilometers is because my speed is written in kilometers. I'm going to leave all those extra sig figs there for now. I'm looking for time, which means time is equal to, okay, distance over time, is equal to distance over velocity. So your distance is 4.0678 times 10 to the 13 kilometers over 600,000 kilometers per hour. You have to ask yourself what unit will you be in at the end, and that will be in hours. So this is divided by 600,000, which comes out to be a massive, massive number. Okay, when you convert this to scientific notation, you'll get 1, 2, 3, 4, 5, 6, 7. You're going to get 6.78 times 10 to the 7 kilometers. And I rounded that incorrectly, actually. It will be 6.8 if you take the correct number of significant figures. And this is in hours. Many things went wrong the first time. Now you can convert that to years if you want. If you want to have a good application, okay, convert that to years. Or you can convert that to, decades. But we'll leave it for that for now. If I ask you so keep that in mind, if I ask you what time unit you need to be in, you need to go to it. If you wanted to go to years here, use dimensional analysis, set up your hours, figure out how many hours are in a day, how many days are in a year. Game over, right? So that's it for the first section. Make sure you master that. You should be very familiar with that formula and the pinhole camera formula. Once you're finished that, go into section 6.2.